Tonight's journey drifts into the realm of Wolf-Rayet stars. These are stripped stellar cores with fierce winds and final burning stages that reshape the space around them. In this calm, science-rich sleep documentary, the story moves from glowing shells and layered interiors to the quiet legacy of heavy elements and dust. If this kind of deep, soothing astronomy helps the mind unwind, please like the video and subscribe for more long-form cosmic sleep stories. Now let the stars soften into silence. A Wolf-Rayet star carries a calm intensity as if a familiar star has been paired to a bright core. The early anchor is simple. Much of the outer envelope is gone, and the exposed layers drive a wind that reshapes the surrounding glow. At this distance, the star does not look like a clean disk. A rough halo surrounds it. The halo is made of gas that streams away in torn translucent veils. A calm promise rests in that motion. The wind is not a detail beside the star. The wind is the star's present tense. In that region, light behaves as pressure as much as illumination. Photons leave hot layers and strike ions in the outflow. Each push is tiny. The total push is steady and large. The effect resembles a dune under a constant gale. Grains lift from the crest and peel away in sheets. Here the grains are atoms and ions. The sheet is a flow of gas that never settles back. The halo shows a physical gradient. It glows hardest near the star. It softens outward as density falls and temperature cools. A simple consequence follows. A stripped star is not only hotter, it is also more exposed to its own light, and that exposure keeps feeding the outflow. The phrase stripped stellar core can stay plain and literal. Stripped means cooler outer layers no longer blanket the hotter interior. Helium-rich material lies closer to open space. In some cases, carbon-rich or oxygen-rich layers also approach the outside. A simple picture helps. The star resembles a layered ember that has lost its ash coat. The ember still has layers. The bright layer sits nearer the surface. That closeness matters because the wind begins where radiation meets matter. The main visual anchor holds steady here. A bright core sits inside a shredded luminous cocoon. The cocoon ripples outward in uneven folds. The folds drift and thin, some brighten, some dim. A boundary is visible in the texture. Close in the glow is smooth and hard-edged. Farther out it becomes lace-like. One core concept holds the launch mechanism. It is a radiation-driven wind. Light carries momentum. When ions absorb and re-emit light, the momentum transfer nudges gas outward. The process repeats again and again. The wind can reach about 2,000 kilometers per second. That is like a storm so fast that the span from Earth to Moon would be crossed in only a few minutes. The number matters because it shows the gas does not fall back. Once gas reaches that speed, it rarely returns. The star spends mass in a steady stream. The halo is the visible trace of that spending. A second concept sits close to the first. The wind is often optically thick near the star. Optically thick means light scatters many times before escaping. In that inner zone, the visible edge is not a solid surface. It is the place where scattered light finally gets out. The edge shifts. It moves outward when the wind densifies. It moves inward when the flow thins. A concrete detail shows up in the halo. Brightness does not fade smoothly. It breaks into faint arcs and darker gaps. Those gaps trace changing density. The arcs hint at curved layers in the flow. Another clear consequence appears. The star can appear larger than its core because the glowing edge rides on a moving wind. The wind does not remain smooth for long. It fragments into clumps and streaks. Dense knots form and drift outward. Long filaments stretch behind them. Some dissolve, some merge. The halo becomes textured like seafoam gathered into patches on a dark tide. This texture is not decorative. It changes how the wind shines. Emission grows stronger in denser gas. A clumpy wind can radiate like a heavier wind that is smooth. That points to a quiet limit of observation. Mass loss is often inferred from the light produced by the wind. If the wind is clumpy, the same brightness can come from less total mass. The true rate can hide behind geometry. The wind also hides behind its own opacity. A signal would be blurred by repeated scattering in the inner flow. The exact launch point cannot be marked as a sharp line. A slow scene returns to the inner wind. Gas leaves the star and accelerates through a steep gradient. The acceleration is not uniform. It rises quickly, then eases as the flow coasts. Close in the wind is hot and bright. Farther out it cools and becomes more transparent. The scale shift is gentle. What begins as a change over a few star radii becomes structure that spans enormous distances over time. In hours, newly launched gas leaves the immediate vicinity. In years, it forms an extended outflow. Over tens of thousands of years, the same outflow can sweep space into a cavity and gather a thin rim. A faint shell can persist long after the core changes state. Another simple consequence settles. When the envelope is missing, deeper composition can appear in the wind. Helium can dominate. Heavier elements can be carried outward as well. The wind becomes a moving record of interior processing. Different ions form in different temperature bands. That creates layered zones in the outflow. Some zones glow closer in. Other zones become visible farther out as the gas cools. The physical detail is a soft stratification. It is not a rigid shell, it is a gradient that shifts as matter expands. The final burning stages in the core remain hidden behind this veil. Yet the veil responds to the core's state. When the core grows hotter, the radiation field strengthens. The wind can thicken. The apparent edge can move. The star can look like a bright kernel wrapped in a shifting cocoon. The cocoon is not a shell at rest. It is a flow that constantly replaces itself. A limit of intuition appears here. Common intuition expects a surface that stays put. A Wolf-Rayet wind replaces the surface continuously, and the visible boundary is a moving compromise. The view settles into a steady image that does not ask for suspense. The bright core remains concealed by a streaming halo. Filaments pull away and fade into colder dark. Light continues to press on matter. Matter continues to flow outward. The next step moves deeper into the wind structure. Clumps and layers appear there. Collisions shape what the outflow becomes. A Wolf-Rayet wind looks like motion, yet its cause begins as quiet structure inside the star. The early anchor is that stripping exposes layers that already exist, and each layer marks a different kind of burning. In that region, a massive star is not a uniform ball of fire. It is arranged in shells nested one inside another. Each shell holds a dominant fuel. The arrangement resembles a calm core sample taken from layered rock. The deeper layers are older and denser. The outer layers are younger and lighter. The difference is not only composition, the difference is also pressure and temperature. Close to the center matter is packed tight. Farther out it is less compressed. A visible clue to this invisible architecture appears in the surface chemistry once the envelope thins. Helium can dominate the outermost exposed layer. Carbon or oxygen can appear closer to view in later stages. The change is like removing a soft blanket from a warm object. Heat leaks more directly into the surrounding space. The exposed layers sit closer to the full force of the core's radiation. That radiation drives mass outward more efficiently. A simple payoff lands early. The same stripping that reveals deeper chemistry also helps power the fierce wind. A slow visual anchor holds on a cross-section image. Concentric shells glow with different intensities. The boundaries are not razor sharp. They are gradients that smear where mixing stirs material. A faint band marks where helium burning dominates. A deeper band marks where heavier elements form. The bands are layered like ripples in a tree trunk, but the rings are made of hot plasma. The physical detail is the boundary itself. It is a region where density and temperature shift rapidly. It is where a small change in depth means a large change in conditions. That steep gradient is why shells remain distinct for long stretches of time. It is also why transitions between stages can be abrupt. The star's interior changes when a fuel begins to run low in a given shell. The next fuel ignites deeper in, or in a new layer. The energy output can shift, the pressure balance can adjust, the outer layers respond by expanding or contracting slightly. Those adjustments can feed into the star's tendency to lose mass. A second payoff settles. Shell structure is not just a diagram, it guides how the star breathes in slow, subtle motions that influence what escapes. The main number can stay simple and safe. The bright life of a massive star lasts about a few million years. That is like a coastline being reshaped by gentle tides across countless cycles while a single wave is gone almost instantly. The scale shift is calm. The star spends most of its life in the long opening act. Then the late burning stages arrive. They proceed faster and faster. The deeper the fuel, the shorter the stage tends to be. The core becomes a place where time compresses. What takes millions of years early on can reduce to far shorter intervals near the end. The outer view remains steady, yet the inner clock accelerates. At this distance, that contrast is one reason Wolf-Rayet stars feel poised near a turning point. The envelope is already reduced. The core is already closer to exposure. The interior stages are already moving toward heavier fuels. Another visual anchor appears in the flow of heat. A bright central region pulses softly in intensity. Around it, shells brighten and dim in a slow rhythm. The rhythm is not a beat. It is a response to evolving balance. Heat rises outward through dense plasma. Opacity changes with temperature and composition. Where opacity is high energy takes longer to escape. Where opacity drops energy moves more freely. Those differences can shape how strongly radiation can press on the surface layers. The core concepts remain few and steady. The first is shell burning, meaning different fuels burn in different layers. The second is stripping, meaning outer layers are removed by winds or interaction leaving deeper layers nearer the surface. A third concept can stay implicit as a detail within the first two. It is the role of opacity in setting where light couples to matter. Opacity is a measure of how easily light passes through material. In a Wolf-Rayet environment, opacity can be high in the inner wind. It can also change sharply with composition. When the star becomes helium-rich at the surface, the set of ions that absorb light shifts. That can change how efficiently radiation drives outflow. A quiet payoff follows. Composition is not only a record of burning, composition is also a control knob for the wind. A concrete physical feature helps anchor this. Near the star, the visible edge is not a fixed surface. It is a scattering layer where photons bounce many times before leaving. The thickness of this layer depends on density. Density depends on mass loss. Mass loss depends on radiation. Radiation depends on the core and on how exposed the core has become. The system forms a loop. The loop does not need drama. It is steady feedback. The more exposed the hot layers, the stronger the push on the wind. The stronger the wind, the more mass is removed. The more mass is removed, the more exposed the deeper layers become. The loop can slow or speed depending on conditions. It can also be interrupted by rotation or by a companion. Those influences can change which latitudes lose mass most effectively. Yet the calm heart of the story remains the same. Layered structure meets stripping. The outer view becomes a projection of an inner history. A limit of observation enters softly. The interior shells cannot be seen directly. They are inferred from light that escapes and from models of stellar structure. The inference is indirect. Many different internal arrangements can produce similar outward brightness and similar wind signatures. Mixing can blur boundaries. Clumping can mimic a denser wind. Rotation can redistribute material in ways that hide the original layering. A signal would carry integrated information rather than a clean map. This is a limit of resolution and a limit of uniqueness. The available light does not always distinguish one interior path from another. The best picture is therefore a family of plausible interiors rather than a single perfect one. That limit does not erase the broad story, it refines it. It encourages safer statements about order of magnitude and about sequence rather than exact timing. Another visual anchor steadies the tone. The star is imagined as a bright kernel surrounded by a translucent atmosphere. Within, shells are nested like quiet terraces. Energy rises through them. At the outer edge, a wind is born where radiation couples to ions. The wind accelerates outward and becomes a long stream. Over time, the stream fills space with matter that carries the star's processed elements. The scale shift always widens again. A small rearrangement in the inner core influences the character of outflow that can shape a bubble far beyond the star. In that sense, structure becomes landscape. The next step moves from the hidden shells to the visible mechanism. Light presses on ions. Lines in the spectrum act like tiny handles for momentum. The wind's acceleration becomes the next calm checkpoint. The Wolf-Rayet wind seems like a bright veil, yet its true engine is invisible and patient. The early anchor is that light accelerates the wind by pushing on countless spectral lines in the gas. At this distance, the outflow does not begin as a rushing storm. It begins as a dense atmosphere that slowly tips into motion. Close to the star, radiation streams outward through a field of ions. Each ion has preferred wavelengths where it absorbs light more strongly. Those wavelengths are like tiny notches in the spectrum. When an ion absorbs a photon at one of those notches, momentum transfers to the gas. The ion soon re-emits, but the outward push remains. This is the quiet mechanism that turns brightness into speed. A small payoff arrives early. The wind does not need explosions. It needs an ocean of photons and a surface layer rich in absorbing ions. A slow visual anchor holds on a thin zone above the bright edge. The gas there looks smooth for a moment, then faint ripples appear. The ripples mark where acceleration grows stronger. Density falls outward. Speed rises outward. The result is a clean gradient. It begins near the star as a heavy, slow flow. It ends farther out as a fast stream. The physical detail is the gradient itself. It is steep near the launch region and gentler later. The wind becomes a moving atmosphere with a built-in ramp. A single main number can stay simple. The wind can reach about 2,000 kilometers per second. That is like a breeze so fast that a trip around Earth would take only a few seconds. The number matters because it clarifies the wind's role. It can outrun most gentle motions in the surrounding gas. It can carve cavities over time. It can also thin itself by expansion until it becomes almost invisible. The main analogy here can remain unique. The spectrum acts like a field of tiny sails. Each absorbing line is a small sail that catches light and pulls matter outward. The sails are not fabric, they are quantum transitions. Yet the image is calm and clear. The more lines available, the more places for photons to push. Wolf-Rayet winds are rich in such lines because the gas is strongly ionized and chemically processed. Helium and heavier elements provide many handles for radiation. Another payoff settles. A wind can be fierce without being hot in the same way as the core. It is fierce because it is efficiently pushed. The motion emerges from coupling rather than brute thermal pressure. A second concept enters and stays close. The wind is not steady in every detail. It can be unstable. Small changes in opacity can amplify into larger changes in acceleration. Where absorption is strong, gas accelerates faster. When gas accelerates faster, it thins. When it thins, absorption can weaken. The push shifts to neighbouring layers. This shifting can create compressions and rarefactions. Dense clumps form. Rarefied gaps widen. The outflow becomes textured not because of turbulence alone, but because the driving itself has a tendency to bunch material. A visual anchor returns in a new scene. Farther out, the wind looks like a bright sheet with faint scalloped edges. The scallops are arcs of denser gas. Between them lie darker lanes where density is lower. The arcs drift outward and slowly stretch. Their curvature changes as they expand. This is a physical boundary made by flow. It is not a hard wall, it is a pattern in density. Another payoff arrives. Those clumps matter because light responds to density. Emission can brighten in clumps. Scattering can also increase. A wind can therefore look heavier than it truly is if clumps dominate the glow. This leads gently into a limit of observation. Many wind properties are inferred from the strength and shape of spectral features. Clumping changes those features. Without direct spatial resolution, different clump patterns can mimic different mass loss rates. A signal would combine light from many clumps at once. The true geometry can remain hidden. Models must assume a clumpiness factor. Different assumptions can shift the inferred mass loss by large amounts. This is a limit of indirect inference, not a failure of physics. It is a reminder that the wind's texture is part of the data. It cannot be ignored. Another calm scale shift appears. The line-driven push occurs on microscopic scales. It depends on atomic transitions and photon interactions. Yet the consequence spreads across enormous distances. In minutes, a parcel of wind leaves the immediate launch zone. In days, it becomes part of a broad halo. In thousands of years, the integrated flow can build a large bubble and a thin rim. The smallest interactions accumulate into macroscopic architecture. The wind carries a memory of its launch conditions outward. That memory is written as density gradients and clump trains. A second analogy helps without repeating the first. The acceleration resembles a traffic flow on a long incline. Cars begin packed close near the base. They spread out as speed increases. A slow car creates a compression behind it. A faster lane opens elsewhere. In the wind, the cars are parcels of gas. The incline is the radiation field. Compressions become clumps. Open lanes become gaps. The image is quiet and mechanical. It keeps attention without urgency. Another payoff lands. If the driving depends on spectral lines, then chemistry controls the wind. When composition shifts, the set of available lines shifts. When temperature shifts, ionization shifts. Both alter how effectively light couples to matter. This is why stripped stars can have winds that differ from those of less exposed stars. The exposed layers present a different mix of ions to the radiation field. The wind is therefore both a consequence and a regulator of evolution. It removes mass. It also changes the conditions for further removal. The section ends with a soft visual. The star's bright core stays wrapped in a veil that continuously renews. A thin inner ramp accelerates gas. Farther out, clumps drift like slow knots in a luminous stream. The next checkpoint moves from how the wind is driven to how it becomes structured. Collisions and clump formation shape the halo and influence what can be inferred from its light. A Wolf-Rayet wind feels smooth from afar yet close in it, breaks into patterns that drift like slow weather. The early anchor is that the wind forms clumps and shells because the driving and cooling naturally create compressions. At this distance, the outflow looks like a bright haze. In the inner regions, it is more like a textured fabric. Bright knots appear. Dark gaps open between them. The overall flow still expands outward. The texture rides on top of that expansion. A calm checkpoint arrives early. Clumping is not a minor wrinkle. It changes how light escapes and how mass loss is inferred. The main visual anchor can be distinct and steady. A thin, glowing ring of denser gas expands outward. Behind it, a second ring follows. Between the rings, the glow dims. The rings are not solid hoops. They are curved shells with uneven thickness. Their edges look scalloped as if the shell has frayed while moving. The physical detail is the shell boundary. It shows a sharper brightness gradient than the surrounding haze. That gradient marks where density rises and where emission strengthens. One core concept holds the formation of clumps. It is radiative instability in line driving. Small differences in absorption create uneven acceleration. Uneven acceleration creates compressions. Compressions create dense parcels. Dense parcels absorb and emit differently than rarefied gas. This feedback makes the texture persistent. Another concept stays close and simple. It is cooling. As gas expands, it cools. Cooling allows some ions to change state. That changes which lines absorb photons. The push shifts, the clumps can sharpen, the gaps can widen, the wind becomes a living pattern, yet it remains impersonal and mechanical. An everyday analogy can stay unique. The wind resembles a pot of thick syrup being pulled into threads as it pours. The syrup does not fall as a smooth sheet. It forms ropes and beads. The ropes stretch. The beads drift. The pattern is set by flow and by the way the syrup resists and yields. Here the resistance comes from radiation coupling and from pressure in the gas. The yield comes from acceleration and expansion. A payoff follows. The same mechanism that drives the wind can also braid it into structure. A single main number can enter safely. A clump can drift outward for about a day before it noticeably changes shape near the inner wind. That is like a cloud that keeps its identity across a long afternoon even as its edges soften. The number matters because it places clumping in time. The wind is not instant noise. It has coherence. Coherence means patterns can imprint on light over measurable intervals. In that region, light behaves as a probe and as a sculptor. The probe part appears in spectral features that change as clumps pass through the line of sight. The sculptor part appears in the way clumps shadow regions behind them from the full radiation field. Shadowing does not make darkness in a visual sense. It makes a reduced push. Gas behind a clump can accelerate differently, he saw. That can create trailing wakes and curved arcs. A new visual anchor appears inside the main one. The leading edge of a shell is bright. Behind it, thin filaments trail like streamers. The filaments curve gently outward as the wind expands. Another payoff settles. Clumps can protect parts of the wind from too much ionization. In sheltered pockets, ions remain in states that absorb strongly. That can sustain driving farther out than a smooth model would predict. It can also enable dust or molecules in rare cases, but the focus remains on structure rather than on chemistry. The texture therefore matters for both dynamics and appearance. The scale shift is calm and wide. The seeds of clumping form on microscopic interactions between photons and ions. The visible shells span distances larger than the star itself by many times. Over years, those shells drift outward and merge into a broader halo. Over thousands of years, the integrated wind can form a large cavity and surrounding gas. The cavity has a rim where swept-up material collects. The rim can become a faint thin shell. The clumps that begin as tiny density bumps end as a sculpted environment. Another concept remains implicit inside the first two. It is porosity. A clumpy wind is porous. Light can slip through gaps more easily. That can reduce the effective opacity in some directions. The wind can look thick and thin at the same time depending on angle and wavelength. This leads softly to a limit of observation. Many wind measurements assume a smooth flow. When clumping is strong, emission lines can exaggerate density because emission often scales with density squared. A small number of dense clumps can dominate the light. A signal would therefore over-represent the densest parcels. The total mass could be lower than the brightness suggests. The geometry also cannot be resolved directly in most cases. The clumps are too small and too distant to be imaged as separate points. The result is a limit in spatial resolution and a limit in model uniqueness. Different clump sizes and filling factors can produce similar spectra. The true pattern can only be bracketed, not pinned. This limit does not remove meaning. It places emphasis on trends rather than exact values. Another payoff arrives. Even without perfect knowledge of clump geometry, the presence of variability and asymmetry reveals that winds are not simple. That complexity helps explain why different Wolf-Rayet stars show different line shapes and different halo appearances. It also suggests that mass loss is not a constant meter reading. It is a living flow with coherent structures. The section returns to the main visual anchor to settle the tone. The expanding ring shells continue outward. Their edges fray. Their brightness fades as density drops. The gaps between shells widen as expansion proceeds. The pattern becomes softer with distance. The next checkpoint moves from structure within one wind to structure where two winds meet. Collisions can carve a sharper boundary and create arcs that stand out even more clearly. When two powerful outflows share the same space, a quiet geometric boundary appears between them. The early anchor is that colliding winds form a curved shock interface that reshapes both flow and light. At this distance, the scene is not a chaotic crash. It is a steady meeting of pressures. Each wind carries momentum outward. Where they meet, neither can simply pass through. A thin surface forms. It bends toward the weaker side. It is like a smooth, curved seam stitched into a moving fabric. The seam is not static. It drifts and flexes as the winds vary. The main visual anchor holds on that seam. A bright arc curves around the Wolf-Rayet star. The arc is sharp on the inner edge. It fades on the outer edge. Behind it, a fainter wake trails outward. The arc is a physical boundary. Density rises across it. Temperature rises across it. The change is steep. The arc is therefore bright. The scene has a calm clarity. A curve marks a balance. A small payoff arrives early. The shape of the arc reveals which wind dominates. A more powerful wind pushes the interface closer to the other source. The arc's curvature tightens where the weaker wind yields. This is pressure geometry made visible. One core concept carries the mechanism. It is a shock. A shock is a thin region of sudden compression. Inner shock speed drops quickly and heat rise. The wind does not stop completely. It is redirected along the surface. The gas flows sideways along the curved boundary. This sideways flow can create a thin layer with its own internal ripples. The physical detail is a double edge. One side faces the Wolf-Rayet wind and is hotter. The other side faces the opposing wind and can be cooler. The interface can therefore show stratified layers. A second concept stays simple. It is cooling behind the shock. Hot gas radiates energy away and becomes denser. Denser gas can fold into a thin sheet. The sheet can fragment into knots. Those knots drift along the boundary. The result is a curved ribbon of bright material with embedded beads. An everyday analogy can remain unique. The interface resembles the line where two streams meet in a river. One stream runs darker and faster. The other runs lighter and slower. Where they meet, a long curved shear line forms. Foam gathers along it. The foam is not the river's whole story, yet it reveals the invisible difference in speed and density. Here the foam is glowing gas, the shear line is the shock surface. Another payoff settles. Colliding winds can concentrate emission into a narrow region. A wide, diffuse wind becomes a bright arc because compression increases density. Density increases radiation. The arc can therefore stand out even when the rest of the wind looks smooth. The main number can be calm and safe. The hottest shocked gas can reach about 10 million degrees. That is like heating air so much that every familiar material would be far beyond any ordinary flame. The number matters because it explains the kind of light that can emerge. Very hot gas radiates strongly at high energies. Yet the region can also be wrapped in cooler wind that absorbs and scatters. The light that escapes depends on viewing angle and on how thick the surrounding wind remains. The scene shifts gently to scale. The shock surface is thin compared to its length. Its thickness can be tiny relative to the curvature radius. Yet its arc can span distances many times the size of the star. In minutes, new wind reaches the interface. In hours, compressed gas streams along the seam. In years, the arc sweeps through space and can seed larger structures in the surrounding medium. A microscopic change in ionization affects radiative cooling. Radiative cooling affects density. Density affects how strongly the arc glows. The scale shift is smooth from atomic transitions to a macroscopic bow shape. A second visual anchor appears without replacing the main one. Behind the bright arc, the wake looks like layered curtains. Each layer is a slightly different density band. The bands flutter as the flow adjusts. The flutter is not random. It follows pressure waves that travel along the interface. Those waves can make the arc brighten in patches. Then the patches slide along and fade. Another payoff lands. The arc can behave as a natural limiter. It channels kinetic energy into heat and then into radiation. It also protects regions behind it from direct wind impact. A sheltered pocket can form on the lee side. In that pocket, gas can cool more efficiently. It can compress into denser clumps than would form in an isolated wind. This is one way colliding winds can create unusually structured outflows. Yet the description remains calm. It is a steady machine of pressure motion and cooling. A limit of observation enters softly. The collision zone is often too small and too distant to image directly in detail. Many properties are inferred from variable emission and from spectral line shifts. Those signals mix contributions from both winds and from the shock itself. If clumping is present, brightness can be dominated by a few dense knots. If absorption is strong, the hottest emission can be hidden and only a softened component escapes. This is a limit of spatial resolution and a limit of line of sight ambiguity. Different geometries can produce similar light curves. Without direct mapping, models remain families of solutions rather than single answers. Another payoff settles. Even with those limits, the curvature and variability constrain the momentum balance. The arc cannot exist without a pressure match. Its position and opening angle encode the ratio of wind strengths. The shock therefore becomes a diagnostic tool even when imperfectly resolved. The scene widens again. The curved seam is a local structure, but its effects can propagate outward. The redirected flows can spiral as the sources orbit each other. The compressed layer can break into fragments that seed larger shells. Over long times, the repeated pattern can imprint a larger scale structure on the surrounding medium. The section ends with a soft transition. The bright arc continues to curve and drift. The wake layers thin into the broader wind. The next checkpoint moves from collision boundaries to the chemical signature carried in the outflow. The exposed core's composition becomes the wind's fingerprint as it spreads into space. The Wolf-Rayet wind carries a quiet signature, as if composition becomes visible only after distance softens the glare. The early anchor is that exposed layers imprint distinct spectral fingerprints, and those fingerprints reveal how deep burning has progressed. At this distance, the wind is not a blank mist. It is a moving mixture of ions. Helium can dominate. Carbon and oxygen can become prominent. Nitrogen can also appear strongly in some stages. The mix depends on which layers are exposed. Stripping is therefore not only a loss of mass, it is a change in what the wind is made of. A small payoff arrives early. Composition is a map of interior history that gets carried outward in a stream. The main visual anchor holds on a calm scene. The star's halo is tinted by different emission bands. Close in the glow looks smoother and whiter. Farther out it separates into faint layered zones. One zone looks slightly brighter in a thin shell. Another zone is more diffuse and fills a larger volume. The physical detail is the layering. It is not rigid. It is a gradient. The gradient marks where certain ions form more readily as the gas cools and thins. In that region, light behaves as both illumination and a filter. Some wavelengths escape easily, some are scattered many times, some are absorbed and re-emitted. The escaping light therefore carries the wind's chemical signature in a complex but consistent way. One core concept can stay simple and defined. A spectral line is light at a specific wavelength from an atomic transition. That is the definition. In the wind, spectral lines appear because ions emit and absorb light at characteristic wavelengths. For an everyday analogy, the spectrum resembles a barcode made of light. Each chemical species contributes its own set of bars. The barcode is not printed on paper. It is painted into the halo by physics. The analogy remains calm and unique. The why matters. If the barcode shifts, composition has shifted. If composition has shifted, deeper layers are nearer the surface. Another payoff settles. The wind is therefore a messenger from inside the star even when the core remains hidden. A second concept stays close. It is ionization. Ionization means atoms lose electrons and become charged. In the hot inner wind, ionization is high. Farther out, as gas expands and cools, ionization can drop. That creates zones where different ions dominate. The zones are not fixed shells, they are moving regions within a flowing wind. A concrete physical detail appears in the form of a transition front. Near a certain radius, the dominant ionization state of an element can change. The emission can brighten or fade across that boundary. The boundary is not a hard wall. It is a smooth band where temperature and density cross a threshold. Another visual anchor appears inside the main one. A faint arc in the halo marks a region of stronger emission from a particular ion. The arc drifts outward as the wind carries it away. The arc thins with distance. It is like a ring of mist that becomes transparent as it spreads. Another payoff lands. When multiple ions contribute, the wind can be probed at different depths. Some lines form close in where density is high. Other lines form farther out where the wind is thinner. This provides a layered view even without a direct image. The main number can remain simple and safe. The wind can travel about 1 light day in roughly a week. That is like a drifting fog bank crossing a wide valley, except the valley is measured in the scale of the solar system. The number matters because it links composition to time. Material seen in the outer halo left the star earlier. Material seen close in is newer. The wind therefore contains a timeline. The scale shift is gentle. Atomic transitions happen in a fraction of a second. The wind's travel time across a light day spans days. The cumulative mass loss shapes the environment over thousands of years. The same helium and carbon that announce interior burning can become part of a broader nebular structure far from the star. Another calm checkpoint arrives. Not all Wolf-Rayet winds show the same chemical emphasis. Some show nitrogen strongly, others show carbon and oxygen more strongly. This reflects different evolutionary stages. In one stage, material processed by hydrogen burning can dominate. In another, helium-burning products can be exposed. The narration can stay plain. The wind's composition shifts as deeper layers are revealed. The shifts are expected. They are not dramatic surprises. They are steps in the arc toward the final burning stages. A limit of observation enters softly and clearly. Spectral signatures do not provide a single direct composition readout. Lines can be affected by density clumping and velocity gradients. Some lines saturate, meaning absorption stops increasing even if abundance rises. Others depend strongly on temperature. The wind can also be optically thick in parts, hiding inner layers from view. A signal would therefore mix regions and biases. Models must disentangle ionization and abundance. Different assumptions about clumping can change inferred abundances. This is a limit of indirect inference and a limit of degeneracy. Several combinations of temperature density and composition can produce similar spectra. The broad trends remain robust. The exact fractions can remain uncertain. Another payoff settles. Even with those limits, certain patterns stand out. Strong helium signatures indicate the hydrogen envelope is greatly reduced. Strong carbon and oxygen features suggest helium-burning products are exposed. These are large-scale statements that do not depend on fine detail. They anchor the evolutionary stage without over-precision. The scene returns to a slow visual to keep the tone gentle. The halo looks like a translucent lantern shade. Within it, subtle bands brighten and fade. The bands are not decorations. They are the wind's chemistry arranged by temperature and expansion. The wind moves outward in steady flow. The chemical fingerprint moves with it. The next checkpoint shifts from chemistry as a signature to chemistry as an agent. When composition and ionization change, opacity changes. Opacity changes how light pushes on the wind. The story returns to the coupling between matter and radiation now, with composition as the quiet lever. A Wolf-Rayet wind can look similar from one star to another, yet small shifts in opacity quietly change everything about its strength. The early anchor is that opacity sets how firmly light can push on the outflow, and composition controls opacity. At this distance, opacity can be felt as a softness in the halo. Where opacity is high, the inner wind looks thicker and brighter. Where opacity is lower, the glow thins and the edge looks more transparent. The physical detail is a changing boundary. The visible edge is a scattering layer. It can move outward when the wind densifies. It can move inward when the flow becomes more rarefied. That edge is not a rigid surface. It is a region where photons scatter enough times to delay escape. In that region, light behaves as pressure because it keeps meeting matter. A small payoff arrives early. When opacity rises, the wind can be pushed more efficiently, even without a change in core power. One core concept can be defined simply. Opacity is how strongly material blocks or scatters light. That is the definition. In plain language, opacity decides how many chances photons get to transfer momentum. If photons pass through too easily, they cannot push much. If photons keep interacting, they keep pushing. An everyday analogy can remain unique. Opacity behaves like the traction between a moving belt and a load. With low traction, the belt slips and the load barely moves. With high traction, the belt grips and the load accelerates smoothly. Here the belt is radiation. The load is the gas. Traction is opacity. The Y matters. A higher grip means a stronger wind for the same brightness. The main visual anchor holds on a calm, slow scene. The inner halo shows a translucent sheath that looks slightly milky. Within it, faint ripples travel outward. The ripples brighten where density rises. They dim where density falls. The milky sheath marks a region where scattering is frequent. It is the wind's inner skin. Farther out, the sheath fades into a clearer flow. Another payoff settles. The inner skin is where momentum transfer is most effective, and small composition changes that can scale up into large mass loss differences. A second concept stays close and limited. It is line opacity, meaning absorption in many spectral lines. In a Wolf-Rayet wind, many ions contribute. Helium and heavier elements provide rich line forests. The lines are like many narrow doors where photons can deposit momentum. If the ion mix changes, the set of doors changes. If temperature changes, the charge states change and the doors shift again. The wind therefore depends on a delicate balance. Too much ionization can remove some useful lines. Too little ionization can also reduce coupling. The wind finds a band where coupling is strong. Another visual anchor appears within the main one. A faint brightness gradient steepens across a thin zone. Inside that zone, the glow is uniform. Outside it, the glow becomes patchy and filamented. The thin zone is a transition in opacity. It is where the wind shifts from very scattering to more transparent. The physical detail is the steepness of the gradient. It marks where photon paths change from long and tangled to more direct. A main number can remain safe and rounded. Near the inner wind, a photon can scatter about 1,000 times before escaping. That is like a single note echoing again and again in a cavern before fading into open air. The number matters because each scatter is a chance to push. Many scatters mean many tiny pushes that sum into a strong acceleration. The scale shift is calm. A single scattering happens in a tiny instant. 1,000 scatters still take very little time in absolute terms. Yet the combined momentum transfer drives gas that will travel outward for days, years, and far longer. A microscopic random walk of light can shape a macroscopic wind. Another payoff arrives. The wind strength is not solely a result of how bright the star is. It is also a result of how effectively the wind couples to that light. This is why two stars with similar luminosity can have different outflows. Their composition can differ, their ionization can differ, their clumping can differ. Each difference alters effective opacity. Clumping is especially important because it changes porosity. A porous wind allows photons to escape through gaps. That reduces the average number of interactions. Reduced interactions mean reduced momentum transfer. Yet clumps also increase local density, which can strengthen line absorption inside the clumps. The result is subtle. The wind can be both more emissive and less effectively pushed depending on geometry. A limit of observation enters softly and clearly. Opacity is not measured directly in a simple way. It is inferred from spectra and from how the continuum and lines form. Clumping velocity gradients and a viewing angle can mimic changes in opacity. A signal would combine information across a wide region. The same observed softness in the halo can result from higher density or from different ionization. Without spatial resolution of the inner wind models must choose a set of assumptions. Those assumptions can shift inferred mass loss and inferred coupling efficiency. This is a limit of indirect inference and a limit of degeneracy. The core story remains stable. Opacity is the gatekeeper for radiation driving. Another payoff settles. Because opacity is a gatekeeper, it also links to evolution. As the star sheds mass and exposes deeper layers, composition changes. As composition changes, line opacity changes. As line opacity changes, wind driving changes. This creates a feedback loop that can either sustain strong mass loss or taper it depending on conditions. The feedback is not a dramatic switch, it is a slow adjustment. The wind becomes a regulator of its own future. The scene widens to keep the tone gentle. The inner wind is a glowing sheath. The outer wind is a thinning stream. Between them lies the transition where scattering gives way to freer escape. Over years, the outflow builds a broader environment. Over thousands of years, it can help sculpt a cavity in a rim. The photon's thousand scatterings are forgotten individually. Their collective push remains written into the shape of the halo. The next checkpoint moves from opacity as a lever to geometry as a lever. Rotation and binarity can reshape where opacity and acceleration matter most, guiding the wind into non-spherical forms without adding any abrupt tension. A Wolf-Rayet wind often seems spherical, yet a gentle spin can quietly tilt the entire pattern. The early anchor is that rotation reshapes density and acceleration, creating an outflow that is stronger in some directions than others. At this distance, the star's halo can look slightly flattened. The brightness can stretch into an oval rather than a perfect circle. The change is subtle. It appears as a gradient that is steeper in one direction and softer in another. The physical detail is the equatorial thickening. Near the star, a denser band can form around the equator. Above and below that band, the wind can look thinner and more transparent. The main visual anchor holds on that band. A luminous belt wraps around the star, is not a sharp ring, is a broad glowing waistline that fades into the polar regions. Fine filaments stream away from the belt and arc outward. A small payoff arrives early. Rotation can guide where the wind finds its easiest path, and that guidance becomes visible as a changing halo shape. One core concept can be defined simply. Rotation is spin around an axis. That is the definition. In a rotating star, effective gravity is slightly reduced near the equator because centrifugal support helps counter the inward pull. The reduction is not an escape. It is a small easing. Yet small easing matters in a system where radiation is already trying to lift material. When gravity is effectively weaker, gas can be launched more readily. When gravity is effectively stronger near the poles, the balance can shift the other way. The result is an outflow with latitude dependence. An everyday analogy can remain unique. The wind pattern resembles water flung from a slowly spinning sponge. Some water leaves uniformly at first. As spin increases, a thicker band forms where the sponge sheds most easily. Here the sponge is the star's outer layers, the shedding is mass loss. The why matters. A directional wind changes how the surrounding environment is sculpted. Another payoff settles. Non-spherical mass loss can leave an imprint that persists long after the star changes. A second concept stays close and limited. It is gravity darkening and brightening in a broad sense. In a rotating star, temperature and brightness can vary with latitude. Poles can be hotter and brighter. Equators can be cooler and dimmer. The details depend on structure and rotation rate. The quiet consequence is clear. The radiation field can also become anisotropic. Where radiation is stronger, driving can be stronger. Where radiation is weaker, driving can be weaker. This competes with the effective gravity change. The wind becomes a compromise between these influences. The compromise can produce either stronger polar flow or stronger equatorial flow depending on parameters. The narration can keep it calm. Different rotating Wolf-Rayet stars can show different asymmetries. A concrete visual anchor appears inside the main one. The belt shows faint curved striations. The striations drift outward like threads pulled from the waist. Each thread is a density enhancement. Each enhancement creates a slightly brighter emission band. The belts and threads are not stable structures carved into solid matter. They are patterns in a flowing plasma. Another payoff lands. These patterns matter because they affect how clumps collide and how shells expand. A denser equatorial region can slow expansion there. A faster polar flow can open a cavity in other directions. The wind can therefore create a bipolar appearance at larger scales, even if the inner star remains nearly round. The main number can stay safe and rounded. A Wolf-Rayet star can rotate in about 1 day in some cases. That is like a glowing beacon completing a full turn between 2 quiet dawns. The number matters because a 1-day spin can allow rotational effects to accumulate steadily. Over many days, the wind experiences a consistent axis. Over years, the integrated outflow builds an environment aligned with that axis. The scale shift is gentle. A rotation cycle is a day. The life stage is far longer. The resulting nebula shaping can persist for thousands of years in surrounding gas. A small daily bias becomes a large-scale pattern. A limit of observation enters softly and clearly. Rotation is not measured directly in a clean way for these stars. The wind's spectral lines are broad because the wind is fast. That broadening can mask rotational signatures. Asymmetries in brightness can also be produced by clumping and by colliding winds in binaries. Without detailed spatial mapping, it can be difficult to separate rotation-driven structure from other causes. A signal would blend effects along the line of sight. The orientation of the rotation axis can also be unknown. If the axis points toward the observer, the halo can look more circular even when it is asymmetric. This is a limit of geometry and a limit of degeneracy. Multiple models can fit similar observations. Another payoff settles. Even with that limit, certain clues can hint at rotation. Persistent asymmetry aligned over time suggests a stable axis. Repeating patterns that match a rotation period also suggest spin. Polarization signatures can hint at non-spherical scattering, though they require careful interpretation. These are not final answers. They are constraints that guide plausible pictures. The scene returns to the main visual anchor to keep the tone steady. The luminous belt continues to glow. Threads peel away and widen as they travel outward. The polar regions remain more transparent. The halo becomes an oval wash of light rather than a uniform sphere. The oval slowly smooths with the distance as expansion dilutes contrast. The next checkpoint moves from rotation to companionship. In some systems, a second star does more than tilt the wind. It can remove the envelope and set the Wolf-Rayet stage in the first place, while also shaping where winds meet and where dust can form. A Wolf-Rayet star can lose its outer layers alone, yet companionship often performs the stripping with a quieter efficiency. The early anchor is that binary interaction can remove the envelope and set the Wolf-Rayet stage, while also shaping the wind into repeating structures. At this distance, 2 bright sources sit within a shared glow. The glow is not uniform. A curved boundary forms where winds meet. A thicker region forms where one star's gravity focuses outflow or pulls material away. The physical detail is a teardrop-shaped distortion in the dense wind. The distortion points toward the companion. It is an elongated region of higher density. Behind it, a trailing stream curves outward. The main visual anchor holds on that trailing stream. It wraps into a faint spiral. Each turn is slightly brighter than the space between turns. The spiral widens as it expands. Its spacing grows slowly with distance because the flow accelerates outward and thins. A small payoff arrives early. Binary motion can turn a steady wind into a patterned record of orbital rhythm. One core concept can be defined simply. Roche lobe overflow is mass transfer through a gravitational boundary in a binary. That is the definition. When one star expands enough, its outer layers can cross this boundary and flow toward the companion. The flow is guided by gravity rather than by radiation alone. It can remove an envelope faster than wind stripping would. The result is a star that becomes exposed. Helium-rich layers appear. The star enters a Wolf-Rayet-like state. An everyday analogy can remain unique. The process resembles water spilling from one connected bowl to another when the waterline reaches a lip. The lip is the gravitational boundary. The spill is guided. It is not sprayed. The why matters. Guided loss can strip the outer layers more thoroughly and earlier changing the future wind and the future explosion type. Another payoff settles. Binary stripping means many Wolf-Rayet stars may be made by interaction rather than by winds alone. A second concept stays close and limited. It is orbital shaping of the outflow. Even after stripping both stars can drive winds. The winds collide and create a curved shock surface. That surface moves as the stars orbit. The motion can imprint a spiral pattern in compressed gas and dust, especially if cooling is effective. The spiral does not require dust to exist in every case. The spiral is a geometry of flow. It can be traced by emission and by density contrast. A visual anchor appears inside the main one. The spiral's inner turns look tight and bright. Farther out, the turns become softer and more diffuse. The physical detail is the brightness gradient along a single arm. It is brighter where compression is strongest. It fades where expansion wins. Another payoff lands. The spiral is a map of where winds meet and where gas cools. It also shows that the outflow is not simply radial. Motion around the system matters. The main number can remain safe and rounded. An orbital period can be about 1 year in some systems. That is like a slow seasonal cycle, except the season is written into a wind made of plasma. The number matters because it sets the spacing of the spiral arms. Material launched over one orbit forms one turn. Over many orbits, many turns stack outward. The scale shift is gentle. The orbital period is a year. The wind travel time across the inner region is days. The spiral can persist and expand for thousands of years as older turns drift outward into the surrounding medium. A repeating rhythm in the inner system becomes a large-scale pattern in space. A small payoff settles. The spacing between spiral turns can indicate the wind speed if the orbital period is known. The wind speed can be inferred if the spacing is measured. This provides a way to connect geometry to dynamics. Yet the narration remains calm and cautious. Many uncertainties remain. The spiral can also be blurred by clumping. It can be distorted by changes in wind strength. It can be bent by motion through surrounding gas. The pattern can be clear in some cases and faint in others. A limit of observation enters softly and clearly. Binary interaction is often inferred from variability and from spectral features that shift in time. If the system is viewed face on Doppler, shifts can be small and hard to interpret. If the system is viewed edge on absorption can hide parts of the flow. The collision zone can be too small to resolve directly. The spiral can be difficult to detect unless contrast is high. A signal would mix wind emission with shock emission and with scattered light. Without a full three-dimensional map, many different orbital inclinations and wind ratios can fit similar data. This is a limit of geometry and a limit of degeneracy. Another payoff arrives. Even with those limits, binarity explains several features at once. It can explain why stripping occurs at lower initial masses than winds alone would require. It can explain repeated arcs and pinwheel-like structures in outflows. It can explain strong colliding wind emission and persistent asymmetry. It therefore becomes a unifying framework for many Wolf-Rayet appearances. The scene returns to the main visual anchor to settle the tone. The spiral continues to unwind. Each arm drifts outward and fades. The inner system remains bright. The outer turns become a faint pattern in the dark. The wind carries composition outward. The orbital motion folds that composition into a structured stream. The next checkpoint moves from geometry to consequence. Repeated outflow patterns can seed bubbles and shells in surrounding gas. Over longer times, these shells set the stage for what the final explosion expands into, shaping the early evolution of the remnant. A Wolf-Rayet wind spends years leaving the star, yet its most lasting work is done in the quiet space it clears. The early anchor is that the wind inflates a hot bubble and sweeps surrounding gas into a thin shell. At this distance, the environment looks like a faint cavity. The cavity is not empty. It is filled with rarefied hot gas. Around it lies a rim. The rim is a compressed shell where swept-up material collects. The physical detail is the shell's sharp inner edge. It marks the contact between hot bubble and cooler, denser gas. The edge can appear as a thin arc. It can also break into filaments. Filaments form where instabilities wrinkle the shell. The main visual anchor holds on the shell. A pale ring surrounds a darker interior. The ring is uneven. Some segments are brighter and thicker. Other segments are faint and porous. The ring has a layered look. The inner side is sharper. The outer side fades into diffuse surroundings. A small payoff arrives early. The wind does not only remove mass from the star, it also builds a prepared stage for whatever comes next. One core concept can be defined simply. A wind-blown bubble is a cavity inflated by stellar winds. That is the definition. In plain language, the wind ploughs into surrounding gas. It shocks and heats. The shocked wind fills the interior as a hot bubble. The bubble pushes outward like a slow piston. Cooler material ahead is swept into a shell. The process is steady. It is not a single blast. An everyday analogy can remain unique. The bubble resembles a soap bubble blown inside a thick fog. The bubble's interior stays clear and warm. The fog is pushed aside into a thin, bright boundary. The boundary is the shell. The why matters. The shell stores mass and can later shape how an explosion expands. A second concept stays close and limited. It is the contact discontinuity. This is the boundary between shocked wind and swept-up shell. The boundary is not a wall. It's a surface where density and composition change abruptly. On the inside, the gas is hot and thin. On the outside, the gas is cooler and denser. The contact surface can be unstable. Small ripples can grow. Fingers of denser gas can intrude inward. Bubbles of hot gas can press outward. The rim becomes corrugated. The visual anchor returns with more detail. Along the ring, small scallops form. Each scallop is a curved fold. The folds drift outward slowly as the bubble expands. The folds can tear into filaments. Filaments can cast subtle shadows in emission. The shadows are not darkness. They are regions of lower density or different temperature. Another payoff settles. The shell's texture is a memory of how steady the wind is. Strong variability and clumping can imprint uneven thickness. Rotation and binarity can also make the shell brighter in some directions. The bubble becomes a three-dimensional record of wind history. The main number can remain safe and rounded. A bubble can reach about 30 light-years across in favourable conditions. That is like enclosing a region wider than a small cluster of nearby stars, even though the wind begins at one source. The number matters because it sets scale. A bubble is a large structure. It is far larger than the star. It is built over time. The scale shift is calm. The wind is launched by atomic interactions in the inner wind. The bubble spans tens of light years. The timescale stretches. In a day, the wind travels outward and thins. In 1,000 years, it can fill a vast volume. In tens of thousands of years, it can sweep a shell into a visible rim. A gentle payoff arrives. The bubble changes the density profile around the star. Near the star, the medium becomes rarefied and wind-shaped. Farther out, the shell becomes a dense wall. This matters later. An explosion expanding into a low-density cavity behaves differently than one expanding into dense gas. The early expansion can be faster. The later interaction with the shell can be sharper and brighter. The wind therefore sets the boundary conditions for the final act. Another visual anchor appears inside the main one. The interior bubble looks faintly mottled. It is not fully smooth. Hot gas can show subtle gradients from center to rim. The gradient reflects how heat and pressure distribute. The outer rim can show a bright thin stripe where cooling is efficient. Behind that stripe, a broader dimmer zone can persist. The physical detail is the layered brightness across the rim. It indicates a compressed cooling region adjacent to a warmer interior. A limit of observation enters softly and clearly. The full three-dimensional bubble cannot usually be mapped completely. The rim seen in projection can hide thickness and depth. A bright arc can be a near segment of a spherical shell or a denser patch in a more complex shape. The interior hot gas can be difficult to detect because it emits faintly and can be absorbed by cooler material along the line of sight. The age of the bubble is also inferred rather than measured directly. Models depend on assumptions about ambient density and wind history. This is a limit of projection and a limit of indirect inference. Several combinations of wind power and environment can produce similar shell sizes. Another payoff settles. Even with those limits, bubbles provide a stable clue. A thin shell implies a long period of wind activity. A fragmented rim implies instabilities and uneven driving. A symmetric bubble suggests a more isotropic wind. An elongated bubble suggests rotational motion through surrounding gas. The bubble therefore connects wind physics to environment. The scene widens to keep the tone gentle. The shell ring surrounds a quieter cavity. The cavity contains the wind's spent energy. The ring contains swept-up material. Over time, the ring can slowly merge back into the broader medium, yet it remains a boundary for a long while. The next checkpoint moves inward again. The star continues its late-burning stages while the bubble expands outward. The interior clock accelerates. The outer environment keeps growing. The next section deepens into how late burning progresses toward collapse while the wind-built environment waits as a calm stage. The final burning stages inside a Wolf-Rayet star unfold behind an outer wind that keeps drifting outward almost unchanged. The early anchor is that the core loses energy through neutrinos, so contraction and new burning phases accelerate toward collapse. At this distance, the outer halo still looks like a steady veil. The deeper interior behaves differently. The core becomes denser. The pressure rises. The temperature climbs. Each step happens because cooling continues even as nuclear reactions struggle to keep up. A small payoff arrives early. The core's fastest changes are driven by an invisible escape route for energy, not by light. The main visual anchor settles on a quiet interior image. The center is traced by nested contours of density. Each contour tightens over time. The spacing between contours shrinks. The inner region looks like a set of shadow rings drawn closer and closer together. The physical detail is the steepening gradient. A small move inward crosses a much larger jump in pressure. That steep gradient is a sign of a core that is compressing while outer layers lag behind. One core concept can be defined simply. Neutrino cooling is energy loss carried away by neutrinos. That is the definition. Neutrinos leave the core with little interaction. Energy departs without strongly heating surrounding layers. The core therefore cools in a way that light cannot imitate. An everyday analogy can remain unique. The core resembles a hot spring that drains heat into porous ground. The surface steam looks steady. The deeper reservoir cools quietly through countless tiny channels. The why matters. Quiet cooling removes support and forces contraction. Another payoff settles. Contraction raises temperature and triggers the next fuel stage. The sequence can be spoken gently without heavy lists. After helium burning, the core moves into heavier fuels. Each fuel releases energy for a time. Each stage ends sooner than the one before. The core becomes an engine that changes gears rapidly. The outer wind continues. The surface chemistry remains a clue. Yet the pace inside becomes compressed in time. The scale shift is calm. What once takes long spans becomes brief intervals. The wind can take days to cross an inner region. The core can evolve through late burning on comparable or shorter timescales. Another visual anchor appears as a supporting scene. A thin shell inside the star brightens in energy generation. It forms a narrow band around the core. The band is not seen directly. It is pictured as a ring of activity in a cross-section. The ring is thin because the conditions for burning exist only in a narrow range. Outside that range, fuel is present but too cool. Inside that range, fuel is exhausted or turned into ash. The physical detail is the narrowness of the band. The ring shows how burning can be confined to a tight layer. Another payoff arrives. Payoff. Shell burning helps hold up outer layers even as the core contracts. The core itself continues to change. As density rises, electrons contribute pressure in a different regime. The core becomes more resistant to compression at first. Then the resistance becomes less effective as the core mass and conditions change. The interior becomes a place where support mechanisms trade roles. The outer wind does not reflect these trades in a simple way. Light from the surface is filtered through the wind. The wind is thick and moving. Variability can appear as small changes in line strength. The core's main story remains hidden. The main number can enter safely and softly. The final stage of burning can last about 1 day in some massive cores. That is like a single slow turn from dawn to dawn, while the rest of the star still seems calm. The number matters because it sets a boundary on warning signs. The interior can race towards collapse while the wind keeps flowing with familiar speed. Another payoff settles. A short final state means the star can cross a tipping point quickly. Neutrino cooling continues through that day. It carries away energy that would otherwise support pressure. The core contracts further. Temperature rises further. The composition shifts toward iron group nuclei in the deepest region. The iron group does not release energy by fusion in the same way. The core then loses a key source of support. The nested density contours tighten again. The inner gradient steepens again. The visual anchor remains the same. The contours become closer. The center becomes more compact. A limit of intuition enters softly and clearly. Neutrinos escape with little interaction, so their passage leaves almost no imprint on the surrounding wind. The core cannot be watched directly through ordinary light. The surface brightness can remain nearly steady even as the core changes rapidly. The wind can also blur subtle signals because scattering and clumping reshape what escapes. This is a limit of observation and a limit of indirect inference. The best picture of late burning comes from models that match broad properties, not from direct interior images. Another payoff lands. Even with that limit, the logic chain remains sturdy. Neutrino cooling accelerates contraction. Contraction raises temperature. Higher temperature enables the next burning phase. Each phase ends faster as neutrino losses rise. The time between stages shrinks. The core approaches conditions where support can fail abruptly. The outer wind continues to carry away mass. That mass loss reduces the envelope. Reduced envelope changes the pressure on inner layers. The whole star becomes more compact and more stripped. The result is a core that is more exposed in a structural sense, even if still hidden behind plasma. Another visual anchor appears to keep rhythm without stealing the main one. A wave of compression travels outward from the deep interior. It does not become a shock at first, it is a gentle pulse in pressure. The pulse reaches the base of the wind-launching region. There it changes density slightly. The inner wind becomes a little thicker for a time. Then it relaxes. The effect is subtle. It is like a tide line moving up and down a beach. The beach is the inner wind base. The tide is pressure adjustment from below. Another payoff settles. Late burning can therefore influence the wind indirectly through slow structural changes without any dramatic flare. The wind can show mild changes in line profiles. The ionization front can shift a little. The scattering layer can move slightly. These are small ripples on a much larger flow. The scale shift widens again. A tiny change in core radius changes pressure at the base. That changes mass loss over hours or days. That mass loss changes the density of the immediate surroundings. Over years, it changes the inner cavity the wind has already carved. The star is therefore shaping the stage even as the stage seems complete. Another limit enters as part of the same boundary. The wind is clumpy and porous. A clump pattern can mimic a change in density. A viewing angle can mimic a change in ionization. Without a full map of the outflow, small variations cannot be assigned to a single cause with certainty. This is a limit of interpretation rather than a limit of physics. The narrative stays calm. The outer view is a veil. The inner view is a tightening set of contours. The two are connected by pressure and by time. The section ends with a gentle transition. The core continues its quiet acceleration. The wind continues its steady escape. The next checkpoint moves from late burning toward the moment when support fails and collapse begins, and how that collapse meets the wind-shaped environment already waiting outside. The surface of a Wolf-Rayet star can look steady while the center changes in a single quiet step. The early anchor is that collapse builds a shock that must cross layered matter and a dense wind before any outward light can respond. At this distance, the outer halo still drifts outward as a pale veil. The deeper interior tightens and then yields. Pressure support fails in the very center. Matter begins to fall inward almost everywhere at once. The movement is not a swirl of fragments. It is a global inward surge guided by gravity. A small payoff arrives early. Collapse is faster than the wind can notice. It happens on a timescale closer to a snap than a season. A central core becomes so dense that it stiffens. The inward flow slams into that stiffening core. A rebound forms. A shock front is born at the boundary where infall meets resistance. The shock is a thin region of sudden compression. It is a moving surface where speed drops and heat rises. The shock starts deep and then travels outward. The main visual anchor holds on that moving surface. It looks like a faint luminous shell advancing through darker layers. Its edge is sharp. Behind it, material is hotter and more pressurized. Ahead of it, material is still falling inward or barely moving outward. The physical detail is the steep boundary at the front. Density changes abruptly across a narrow region. The gradient is so steep that a small step in radius crosses a large change in state. Another payoff settles. The shock is not guaranteed to coast easily. It must spend energy breaking apart heavy nuclei and lifting matter against gravity. That cost can slow it. The shock can stall. It can become a standing boundary rather than an outward racing wave. Here the story remains calm. The interior is a competition between pressure and weight. Energy tries to move outward. Gravity tries to pull inward. A second core concept enters with a simple definition. Shock breakout is when a shock reaches a layer where light can escape quickly. That is the definition. Before breakout, photons are trapped. They scatter and scatter again. They cannot carry news to the outside. The shock can be present and powerful while the exterior looks unchanged. When the shock reaches a thinner region, the trapped light finally escapes. The escape can be brief and bright. The everyday analogy stays unique. The process resembles a strong wave travelling under a thick ice sheet on a lake. The wave moves fast beneath, the surface stays quiet. When the ice thins near the edge, the wave can lift and crack the last layer. The hidden motion becomes visible, the why matters. Breakout sets the first outward sign of collapse in light. A main number can enter safely. The core collapse itself can unfold in about 1 second. That is like the time a raindrop takes to fall past a leaf edge. The number matters because it shows the mismatch in clocks. The wind evolves over days and years. The core changes in a blink. The scale shift is gentle. Nuclear reactions happen in tiny instants inside nuclei. The collapse happens in 1 second across a region the size of a planet. The outward consequences then unfold across light days and light years. Another visual anchor appears to keep rhythm. In a cutaway view, layers near the center look like tightly packed bands. The shock runs along those bands. Each band has a different composition and density. The shock refracts through them in a loose sense. It speeds up in lower density regions, it slows in denser ones. The physical detail is the changing curvature of the front. It can become slightly distorted by uneven structure. It can also spawn turbulence behind it. Turbulence is not shown as violence, it is shown as a soft, rolling texture. Another payoff arrives. Layering matters because it controls how the shock spends energy. A dense layer can drain the shock. A thinner layer can let it recover speed. The shock therefore carries the imprint of the star's interior structure. The wind outside adds another layer of influence. A Wolf-Rayet wind is thick near the star. It can be optically thick for a time. It can act like an extended photosphere. In that region, light behaves as a trapped gas. It diffuses outward rather than streaming freely. If the shock reaches the base of the wind, the breakout can occur not at the solid surface but within the wind itself. The main visual anchor shifts outward without changing. The luminous shell reaches a fog-like outflow. The shell keeps moving. The fog glows briefly along a narrow layer. The glow then spreads into a broader, softer illumination. Another payoff settles. A dense wind can turn a sharp flash into a longer, smoother brightening. It can also change the color of the emission by absorption and re-emission. The light can look as if it comes from a larger radius than the star's core would suggest. The physical detail is a scattering layer that expands as it brightens. The edge of that layer is rounded. Its brightness declines gradually with distance. It resembles a glowing mist boundary that drifts outward. A limit of observation enters softly and clearly. The central collapse and the earliest shock motion are hidden from ordinary light by extreme opacity. Only the later stages of breakout and the responsive outer layers can carry information outward. Even then, wind clumping and asymmetry can blur the signal. A signal would mix emission from different radii and times because photons take different paths. This is a limit of direct access and a limit of inversion. Many different interior histories can produce similar outward light curves once reprocessed by a wind. Another payoff lands. Despite that limit, certain constraints remain firm. A faster rise suggests a more abrupt release or a thinner overlying layer. A slower rise suggests diffusion through a thicker wind. A higher early brightness suggests a larger effective emitting area or stronger heating. These are not precise diagnoses. They are stable directional clues. The environment built by the wind also matters now. The bubble and shell carved earlier provide a staged density profile. First comes a dense inner wind. Farther out lies a lower density cavity. Beyond that, consider denser swept-up shell. As the outward blast expands, it first interacts with the wind close in. Then it enters the cavity and can coast more freely. Later it can meet the shell and decelerate strongly. The scale shift widens again. Minutes to hours shape the first light. Days to months shape the early expansion. Years to centuries shape the remnant and its interaction with the shell. The same collapse that takes 1 second can set a story that lasts far longer than the wind phase itself. Another visual anchor arrives to keep the cadence gentle. The expanding front moves through the wind like a bright tide line moving across sea mist. The mist brightens where the front passes, it then settles into a softer glow behind. The front keeps widening. Its surface becomes a larger and larger sphere. Its brightness becomes more even. Its edge becomes less sharp as diffusion and expansion smooth it. Another payoff settles. The wind is not only a backdrop, it is a filter and a resistor. It can store energy briefly in heat. It can convert kinetic energy into radiation at shocks. It can create early emission that is dominated by interaction rather than by the interior alone. The section ends with a gentle transition. The outward front continues to expand into the wind-shaped space. The next checkpoint widens to the longer aftermath where the blast meets the larger bubble and shell, and where the final products of burning are mixed into the surrounding medium. The blast from a Wolf-Rayet collapse does not expand into emptiness. The early anchor is that the outward shock first runs through a dense wind and then enters a wind-blown cavity with a waiting shell at its edge. At this distance, the bright front looks like a growing sphere with a textured rim. The rim is not smooth. It shows knots and dim gaps. It shows thin filaments that curve and reconnect. The physical detail is the sharp outer boundary where density jumps across a narrow layer. Behind that boundary, the interior glows more softly. Ahead of it, the wind-shaped space stays darker and quieter. A small payoff arrives early. The earlier wind phase becomes a map that tells the shock where to slow down and where to glide. The main visual anchor holds on a moment of contact with the cavity wall. A faint ring appears in the darkness. It is the swept-up shell that the wind built long before. The expanding front approaches it. The front is broad and bright, the shell is thin and pale, yet. When they meet, the shell brightens in a narrow band. The band wraps around the cavity like a bracelet of light. The bracelet is uneven. Some sections flare more. Some sections remain faint. The contrast reveals where the shell is thicker. Another payoff settles. The ring marks a boundary between two regimes of expansion. Inside the cavity, the shock travels quickly because density is low. At the shell, the shock spends energy compressing denser gas. The expansion rate changes. The shape can also change. A dent can form where the shell is thick. A bulge can form where the shell is thin. One core concept can be defined simply. A forward shock is the leading compression wave moving outward into surrounding gas. That is the definition. The forward shock heats what it encounters. It compresses it into a thin layer. The thin layer can radiate and glow. The glow depends on temperature and density. In a cavity, the layer is thin and faint. In a dense wind or shell, the layer becomes brighter and thicker. An everyday analogy can remain unique. The forward shock resembles a storm front sweeping across a calm sea and then meeting a line of steep cliffs. Over open water, the front advances smoothly. At the cliffs, the air piles up and brightens into a sharp edge of cloud. The why matters. The location of brightening reveals where the surrounding medium changes abruptly. Another payoff arrives. The bright ring at the shell tells that the wind phase truly shaped the environment on the large scales. A second concept stays close and limited. It is the reverse shock. As the forward shock plows outward, the interior ejector is not left untouched. Pressure builds behind the leading front. That pressure sends a compression wave back inward into the expanding ejector. This reverse shock heats the ejector. It can make inner layers glow later. It can also slow and mix clumps. The physical detail is a second boundary inside the remnant. It is less sharp than the outer rim. It appears as an inner arc or a diffuse band. It can flicker in brightness as clumps cross it. Another payoff settles. The reverse shock is a quiet recycler. It takes fast-moving ejector and turns part of that motion into heat. It also reveals composition indirectly through how cooling proceeds. The main number can enter safely. The remnant can take about 1,000 years to cross a large, low-density cavity in some cases, like a millennium of slow seasons passing while a single structure keeps growing. The number matters because it links a brief collapse to a long visible phase. The scale shift is gentle. The core changes in about 1 second. The remnant evolves for 1,000 years as it expands and cools. Over that time, small clumps become large features. A knot that begins as a compact overdensity can stretch into a filament. The filament can span a large fraction of the remnant radius. The visual anchor returns with fine detail. The bracelet on the shell becomes braided. Thin strands split and merge. Brightness peaks where strands cross. Dark lanes form between them. The lanes are not empty. They are lower density pockets and cooler regions. The outer rim also shows scallops. Each scallop is a curved indentation. The indentation marks where a dense patch in the shell slows the shock. Another payoff arrives. The shell is not a uniform wall. It is a patchwork built from instabilities during bubble growth. That patchwork forces the shock into a lumpy geometry. The lumpy geometry then drives mixing. Where the shock decelerates, fingers of dense gas can push inward. Where the shock races ahead, hot gas can slip around obstacles. The remnant becomes a stirred volume. It is stirred without any solid paddles. It is stirred by pressure gradients and by shear. The narrative keeps its calm. Mixing does not mean chaos without pattern. It means structures exchange positions and blend. A faint interior haze appears as the reverse shock heats ejector. The haze is not uniform. It concentrates in arcs. It gathers around knots. The physical detail is the layered appearance. An outer rim glows from shock surroundings. An inner band glows from shocked ejector. Between them lies a softer region where density is lower. Another payoff settles. Layering hints at origin. Outer layers reflect swept-up wind and shell. Inner layers reflect material from deep inside the star. The two meet in places where fingers intrude. Those places are where mixing is strongest. A limit of intuition enters softly and clearly. The remnant is three-dimensional, yet it is seen as a projection. Bright filaments can overlap in line of sight. A thin arc can be a sheet seen edge on. A knot can be a long filament seen end on. Density and temperature are inferred from emission and absorption not measured directly. The ambient density of the cavity is also uncertain. The thickness of the shell is not known everywhere. This is a limit of projection and a limit of model dependence. Several combinations of cavity size and density can produce similar ring brightness and similar expansion rates. Another payoff lands. Even with that limit, some relationships stay stable. A sharper, brighter ring suggests a denser shell. A smoother rim suggests a more uniform cavity wall. A strong inner band suggests a reverse shock that has moved deep into ejector. A weak inner band suggests the reverse shock remains farther out. These clues do not give a single answer. They narrow the range of plausible histories. The scale widens again. Over 1,000 years, the remnant moves from early interaction with dense wind to later interaction with the cavity wall. Over many thousands of years more, it can begin to fragment the shell. Pieces of the shell can be accelerated outward. Other pieces can fall inward as dense knots. The cavity that once felt empty becomes filled with a complex foam of hot gas and cool fragments. The wind that once looked like a smooth veil is now part of a layered environment. Another visual anchor appears to keep rhythm without replacing the main one. A faint shadowed interior shows drifting rounded clouds of denser gas. They float within a brighter haze. The clouds are not buoyant in a simple sense. They are carried by pressure and turbulence. Their edges are softened by heating and ablation. The physical detail is the trailing wake behind a knot. It looks like a comet tail of brighter emission. It points away from the direction of motion. Another payoff settles. Wakes show that dense knots are being eroded and mixed into the hot flow. This is one way heavy elements spread into the larger medium. The section ends with a gentle transition. The remnant continues to grow and cool as it presses on the shell that the wind built. The next checkpoint widens further to the long perspective where the dispersed elements and the altered surroundings settle into a quiet legacy across much longer timescales. A Wolf-Rayet ending leaves behind a quiet signature that keeps changing long after the first bright moment fades. The early anchor is that heavy elements and dust change how gas cools, so the surroundings evolve in a new direction. At this distance, the remnant looks like a dim sphere with a bright rim. Inside it, the glow is softer. The rim is sharper. The boundary is where compression is strongest. The physical detail is a thin skin of shocked gas. Its edge is a steep gradient in density and temperature. That steep edge is the place where energy turns into structure. A small payoff arrives early. The explosion is not only a burst of light, it is a chemical and thermal reset for nearby gas. The main visual anchor settles on a scene of cooling layers. The outer rim becomes lace-like. Filaments form, they curve and braid, dark gaps open between them. The dark gaps are cooler pockets. The filaments are warmer sheets seen edge-on. As the remnant expands, the filaments stretch. Their spacing grows. Their contrast softens. The interior begins to show a faint mottling. It looks like mist with embedded threads. Another payoff settles. Filaments form because cooling is not uniform. Dense regions cool faster. Cooler regions compress and become denser still. This feedback turns a smooth shell into a textured one. One core concept can be defined simply. Metallicity is the fraction of matter that is not hydrogen or helium. That is the definition. In a Wolf-Rayet remnant, metallicity is high in the ejector. It is lower in the older windswept shell. When the two mix, the local metallicity becomes patchy. Patchiness matters because it changes cooling. Heavy elements provide many ways to radiate energy. Gas with more heavy elements can cool faster at the same temperature. A unique, everyday analogy can remain gentle. The remnant is like a drifting plume of volcanic ash entering a clean cloud layer. The ash does not shine. It changes how the cloud holds heat and how droplets form. The why matters. Faster cooling can turn hot gas into cooler clumps. Cooler clumps can survive and travel farther. Another visual anchor appears to keep rhythm. Along the rim, a narrow band brightens and then dims. The band is thin. Its brightness is strongest where density is highest. It fades where the shell is more rarefied. The band slowly shifts outward with expansion. Behind it, a softer glow fills a thickening volume. The physical detail is layering. A bright skin sits on a fainter interior. The thickness of the faint interior grows over time. Another payoff arrives. Layering shows that energy is leaving the gas and that the remnant is moving from a hot stage to a cooler stage. A second concept enters with a simple definition. Dust is solid grains that form from cooled atoms in gas. That is the definition. Dust can form when gas becomes cool enough and dense enough. In a remnant, dust is not evenly spread. It forms in sheltered regions, it forms in dense clumps. It forms where cooling runs ahead of expansion. When dust appears, it changes light transport. It absorbs some light. It re-emits at longer wavelengths. The remnant can develop dark lanes where dust gathers. Those lanes are not empty. They are filled with grains and cooler gas. Another payoff settles. Dust becomes a memory of where the gas cooled fastest. It marks the history of compression and mixing. The main number can enter safely. About 1 solar mass of heavy elements can be dispersed in some such events, like releasing the mass of a small star into the surrounding gas. The number matters because it sets the scale of enrichment. It is enough to change the chemistry of a large region if it mixes widely. The scale shift is calm. A grain can be smaller than a cell. A remnant can be tens of light years across. The same event links the smallest solids to the largest cavities. Another visual anchor appears as a supporting scene. In the interior, clumps drift outward. Each clump has a brighter edge and a dimmer core. The edge is where it is heated by surrounding hot gas. The core is cooler and denser. Some clumps trail faint wakes. The wakes are thin. They curve gently. They show where material is being stripped and mixed. The physical detail is the wake shape. It narrows with distance. It fades into the background glow. Another payoff arrives. Wakes show that mixing is not instant. It is a slow erosion. It is a steady exchange between clump and flow. This slow exchange matters for chemistry. If clumps survive, heavy elements remain concentrated. If clumps are shredded, heavy elements spread more evenly. A limit of observation enters softly and clearly. Cooling and dust formation happen in regions that are small compared to the remnant size. They are also hidden behind projection. A dark lane can be a thin sheet viewed edge-on. A bright filament can be a folded surface. The true three-dimensional distribution cannot be read from a single view. In addition, the density of the surrounding cavity is uncertain. That uncertainty changes estimates of how much mass is swept up. It changes estimates of how quickly the remnant cools. This is a limit of geometry and a limit of inference from light alone. Another payoff lands. Even with these limits, the direction of change is stable. More heavy elements mean more efficient cooling. More cooling means more structure. More structure means more places for dust to form. Dust then changes radiation flow and helps gas become even more uneven. The remnant therefore acts like a sculptor that uses heat loss as a chisel. The outer rim keeps moving outward. The interior keeps softening. Over time, the remnant merges into the larger medium. Its sharp edges blur. Its filaments fade. Its clumps either dissolve or join colder clouds. The scale widens again. The event begins with a core change faster than a heartbeat. Its chemical signature can persist for millions of years as enriched gas circulates through a region. The wind-blown bubble that once felt like a cavity becomes part of a larger network of hot and cool phases. The heavy elements become part of future molecules. The dust grains become seeds for new solids. Another visual anchor arrives to keep cadence. Far from the center, a faint arc of compressed gas glows softly. Behind it, a wider haze carries thin strands. In the haze, a few darker streaks mark dust-rich regions. The streaks drift and broaden. They soften into the background. The physical detail is the gradual smoothing of contrast. Sharp becomes rounded. Bright becomes diffuse. Another payoff settles. The long legacy of a Wolf-Rayet star is a change in how gas behaves, not only a brief flash. The section ends with a gentle transition. The remnant continues to cool and mix. The enriched gas continues to spread. The next checkpoint gathers the whole arc into a quiet perspective where stripped cores, fierce winds, and final burning stare settle into a calm, coherent picture. The last view of a Wolf-Rayet star is not a single moment. The early anchor is that stripped cores, fierce winds, and final burning stages connect through pressure and flow. At this distance, the scene begins with quiet geometry. A bright, compact source sits at the center of a wind-shaped space. Around it, a faint halo shows the wind's reach. The halo is not uniform. It has a gradient brighter closer in and dimmer farther out. The physical detail is that gradient. It is a smooth fading that records how density falls with radius. A small payoff arrives at once. The wind is not decoration, it is the outer expression of an exposed interior. The strongest wind belongs to a core that no longer hides behind a thick envelope. The main visual anchor settles on a slow rotation of perspective around the wind bubble. The bubble is not a perfect sphere. It looks slightly pinched along one axis. Along its boundary, a thin shell appears as a dim ring. The ring has scalloped edges. Some arcs are sharper, some arcs are washed out. The ring is the compressed wall built from swept-up gas. The interior is the low-density cavity carved by wind over long time. Another payoff settles. A wind bubble is a fossil of the star's late life. Its size and shape encode how long the wind blows and how steady it is. The first core concept can be named with a short definition. A stripped core is a star's inner layers exposed after mass loss. That is the definition. Exposure matters because it changes what pressure can drive outward. It also changes what layers are available to be thrown away. A unique, everyday analogy can remain calm. A stripped core resembles a lantern with the outer shade removed. The inner light does not become new light. It becomes more direct. The surrounding air feels the heat more strongly. In the same way, the exposed layers affect the surrounding medium more directly. The why matters. Direct influence means the surroundings are prepared before the final collapse happens. Another visual anchor appears to keep the rhythm without replacing the main one. The wind itself becomes visible through motion. A thin veil of gas flows outward. It looks like a slow tide across the cavity. The veil is not smooth. It shows knots and faint streaks. The streaks mark clumps in the outflow. The physical detail is the streak texture. It suggests instabilities and changing conditions in the wind. Another payoff arrives. Clumps matter because they seed later structure. When a shock arrives, it does not meet a uniform medium. It meets a landscape of dense islands and thin channels. The second core concept enters with a short definition. A stellar wind is a continuous outflow of gas driven from the star's surface. That is the definition. In a Wolf-Rayet phase, the wind is strong and persistent. It carries away mass. It carries away angular momentum. It also carries momentum that pushes on surrounding gas. The wind creates a cavity. It piles up a shell at the edge. The shell becomes a boundary where density rises sharply. That sharp rise later shapes any shock that passes through. Another payoff settles. The wind is a long, slow engine. It spends its power over hundreds of thousands of years. It sculpts space more than a brief flash can. The third concept stays within the limit of 3. It is the final burning stages. In those stages, the core fuses heavier elements in nested shells. The nested shells are layered like an onion. Each shell is thin compared to the whole star. Each shell burns for a different duration. Some shells last for thousands of years, some last for days. The scale shift is gentle. The wind works for hundreds of thousands of years. The deepest changes in the core can happen in days. The collapse can occur in about 1 second, like a single beat in a long, quiet song. That number is the main one. It matters because it shows how a long preparation ends in a rapid transition. Another visual anchor arrives in soft focus. Near the center, the inner region becomes denser. The glow changes tone. It becomes steadier. The surrounding wind still flows outward. The boundary shell still holds its scalloped rim. The contrast between stillness and flow is a physical clue. The core evolves inward while the wind continues outward. Another payoff arrives. The star connects 2 timelines at once. A short core timescale triggers a long environmental response. A limit of intuition enters in a quiet and specific way. The final burning layers are not seen directly. Their structure is inferred from models and from indirect signals. The wind density is also inferred from emission and absorption. Projection hides 3-dimensional shape. A ring can be a shell, a filament can be a sheet seen edge-on. Multiple histories can produce similar wind bubbles. This is a limit of indirect inference and a limit of degeneracy in models. Another payoff settles. Even within those limits, certain connections remain firm. Strong winds require strong radiative driving and an exposed core. Exposed cores require heavy mass loss. Heavy mass loss changes the pre-collapse environment. The pre-collapse environment then shapes how a shock expands and cools. The chain holds even if details vary. The narrative returns to the broad arc. Early in the story, strip cores appear as compact bright sources with unusual spectra. Then winds dominate as thick outflows with dense edges. Later final burning stages build layered interiors that are short-lived and decisive. Finally, collapse injects energy into a medium already shaped by wind. The remnant expands into a cavity. It meets a shell. It becomes filamentary. It cools. It mixes heavy elements and dust into surrounding gas. Each step fits into a single continuity. Another visual anchor appears to ease toward rest. The remnant is now faint. Its rim is a soft circle. The circle is not perfectly even. It has gentle brightness variations. The interior glow is like mist. Filaments are barely visible. Dark lanes soften. The physical detail is the fading edge. The gradient becomes less steep. The boundary becomes less sharp as it merges with the larger medium. Another payoff arrives. A Wolf-Rayet life ends by dispersing structure into larger quietness. It leaves behind a slightly enriched region. It leaves behind a reshaped cavity. It leaves behind a memory written in gradients and rings. The scale widens one final time. A single star alters a region for millions of years. The region then becomes part of a galaxy-wide circulation of matter. Over longer spans, enriched gas can join new clouds. New clouds can form new stars. The chain does not require a repeating cycle to be meaningful. It only requires that matter keeps moving and changing state. The close comes gently. The wind bubble the shell and the fading remnants settle into the background of the interstellar medium. The last impression is of slow expansion and slow blending. The story remains in calm motion. The scene moves outward into quieter space and steadier darkness.